So what we're going to do today is just finish up what we have left in the notes, and then do a little review. We'll go over the problems in the practice exam. So y'all know your exam 2 is Wednesday night, and right here is where you should go. So, by the way, our final schedule here for everyone is the first day of finals, first final for online and in person, and if you want to take a conflict, it's the same day at night. Not if you want to take a conflict. I can't be as flexible if you really have a conflict. If you have an official conflict, either 3 consecutive exams, or for the online people, you might have another exam scheduled at this time. All right. Any questions on that? All right. So let's go to the document camera and get going. So where we left off last time was looking at something called post-hoc tests. So the idea is this: if you're looking at a bunch of pairwise differences after you've already done the significance test for and notice that there is at least one difference among these groups. Remember, we're comparing the averages of a few groups here, 3 or more, and if you see that at least there is some significance because you did the overall test with the chi-squared or the F, and it was significant. So now you're testing, in this case, we were testing to see which, we know there's at least one difference, which one of these pairwise differences, which one of these differences between these groups is significant. And so we decided to test. We saw this big difference between blacks and Hispanics. We looked at the data. After looking at the data, we noticed this. We saw what the averages were, right? And we took the biggest and the smallest and said, why don't we test that for significance? So we sort of cherry-picked that out. So we do our usual pairwise. If you're going to compare the average of 2 groups, what we always do is we take the difference between them, between their means, right? We expect it to be 0. That's the null. We want to see if you're always going to get some difference. The question is this significant or not? I mean, you're not going to get exactly the same thing, exactly the same average. So the question is this difference of 1.795 in averages big enough to think that it's actually significant, that it's not just due to random variation? So we have to compare it to what? Random variation. The typical variation you'd see, the sampling error, the difference in the sampling error between the 2 averages. The typical variation you'd see if you randomly did this over and over and over again. That's called the standard error of the difference here. And you combine them by squaring each standard error and then taking the square root. But after you simplify it, you get this very easy on the next page, assuming we have the same standard deviation for both groups but different ends, right? Then it boils down to this. So this standard error plus here of the errors is an estimate. We're going to use this as an estimate for the standard deviations of each of these groups, the standard deviation plus of each of these groups. You can see that they vary, but we're going to use this as our pooled estimate because if you recall, one of the assumptions of doing this, ANOVA, is that they all have equal variances. Okay? So we're going to use this right here, so that makes it really easy. So you're just going to divide by the standard error, like right here. You take the difference, you divide it by the standard error, and then you have to weight it according to the different sample sizes here. The 2 groups have a sample size of 84 and 99. So we did that, and we got this big t-statistic, and we found the degrees of freedom, since they're based on the entire, all the whole sample, it's going to be n, which was 858, minus the number of groups. So that's the degrees of freedom. All right, so we did that. And then, sorry, we didn't finish yet. We got this really small p-value, right? And you'd think you'd just be done. This is just what we've, this is just nothing new up to this point right here. You'd think you'd just be done right here. Because you've done pairwise differences, 2 samples of your t-test back in Stat 100 or back in AP Stats. This is nothing new here. Your observed difference over your standard error for the difference. The only thing that's new is we have to multiply it by some correction here. And the one we learned is the Bonferroni correction. There's lots of different ones, but the one that we've learned is the Bonferroni. Why do you have to do that? Because we have to do that because we cherry-picked out a difference after looking at the data. Okay? So the idea is this, that the p-values, let's look here. Maybe if we go through it here, you'll see more. Let's just fill this out so you'll see what we did here on page 123. So what we did was we look at all these differences here. There's 5 groups. So we said there's 5 times 4 pairwise differences, right? But we don't care about order, so we divide by 2. In other words, comparing whites and blacks is the same as blacks and whites. So here we have the 10 pairwise for 5 groups. You'd have, for 5 groups you have G times, for any number of groups, G times G minus 1 over 2. So in this case we have 10. All right? And what did we do? We're picking out, among these 10, we're picking out one particular difference. If we had said ahead of time, this is the difference we're interested in, we think this is going to be significant, well, then we wouldn't have to make any adjustment if we did it prior to looking at the data. Because think about it, if there were 100, take it to the extreme, if there were 100 differences, right, just by the luck of the draw, you'd expect to get, even if there's absolutely no, let's say you just took, randomly divided a population to, so that there were 100 pairwise comparisons. And there really was nothing, there weren't any groups at all. You just made, enough divisions so that there were 100, right? And there's nothing, there's no different, you're just randomly dividing a population. Then wouldn't you expect some of them to be different than the others just by chance? And by definition, 5% of the time you're going to get significance. Because we say 5% of the time, that's what you'll get when nothing's going on. Does that make sense to you? Does everybody understand that, or do they need to explain further? Anybody? Okay. So we got that, and we have this observed difference here. That's our observed difference. And here, right here, is our standard error for the difference. Right here. And when you divide those two, you get this t-statistic. That's what we got. This divided by that equals that. And we got this p-value here. Okay? But this p-value is corrected. It's multiplied by the number of groups. Because the p-values are all multiplied by 10 here. You can see some of them are over 100%, right? They're all multiplied by 10. Why? It's because we performed 10 tests and didn't specify which of the 10 differences we'd expect to be significant. Imagine performing 100 tests. You'd expect 5% to be significant just by the luck of the draw. By definition, that's what we mean. So the Bonferroni method adjusts the p-value by multiplying by the number of pairwise comparisons, right? Okay. Okay, and they're all two-sided tests because we didn't specify ahead of time anything. We're just looking for a difference. All right, so just to remind you, let's just do this again. How did we get all this? We got this observed difference right here. And this I think you know, but we'll write it down. We got this observed difference because it was just the difference between the two averages. That was 3.643 for blacks minus 1.843 for Hispanics. Then this right here, how did we get that standard error? That's the standard error plus for the difference, and we got that by doing what? We took this 3.18, which you're going to be given. That's the SD plus errors, and you'll be given that. And then we just multiplied it by what? The square root of 1 over the sample size for the blacks plus 1 over the sample size for the Hispanics. Okay, so that was N for the black group, and this is N for the Hispanic group. And that's all we did. And that's how you got this. And then the T was just 1.794 divided by that. And that's how we got that. And then we multiplied so that's all we're doing here. Any questions on that? All right. So you're good on that, and so let's move on. If you want to see how the Bonferroni correction works out mathematically, I explain it here, but you can read that on your own. If you just want to see how it actually works out, it's a very conservative estimate. This is on page 124. So you can just see how the math works out if you want to read that. And now we're on page 125. And I just want to make it clear, you already answered this in your homework, but I just want to make it clear that there's basically two ways we can do this, depending on when we make our hypothesis. All right? If we single out before looking at the data, then we can just do our usual p-value. We don't have to make an adjustment. Like next time we do this, let's say I now have this hypothesis that blacks are more conservative than Hispanics on this. And I do the survey again. Well then, and I make that, I say that's the difference I'm going to look at ahead of time. Then I don't have to do any correction. The second time you do it, you have more information now. So if we wanted to retest this, we could do it, we wouldn't have to multiply by 10 or by anything. Okay? But if we single out after looking at it, then we have to use this correction. Okay? And it reduces the probability of these false positives. Because remember, if you don't do a correction and you had 100 tests, then, and you look through them all, then, and look for the 5 biggest differences, well, then you're just about always going to find something significant. I mean, not typically, you'll find at least 5 significant at the 5% level. And so you'd have a lot of false alarms. You'd find differences where none exist, really. And that's the type 1 error. All right. So now we're done with that. And the assumptions for ANOVA, I don't think we have to go through them because ANOVA, as you saw, is a special case of regression. Just a special case of regression where the X predictor is a categorical variable. That's all it is. So it's going to be the same as regression, the same exact thing. All right? And when you come back from break, we're going to look at these assumptions much more carefully, and we'll look at violations and what of these assumptions and what we do when there's violations. Okay? Well, for now, we can look at one way to deal with that, and this is the randomization test, which we've already done. our assumptions don't have, we don't have to, this doesn't depend on any, that our data comes from any kind of known distribution, because we're going to enact randomization. So this is basically the same as in chapter 22, but we might as well, let's go over it in this context. And the first thing you might say is, hey, and certainly in the Stat 100 data, we do not have a random sample, unless we randomly sample 100 out of that big population, or like you did on your homework. But if we look at the whole class, we don't have a random sample. So what are we doing? That's a violation of our very first assumption. You know, that we have randomization. Okay, so technically we can't do a significance test, but people do them all the time anyway. And here's the thought process, and you should really think about this for no matter what you're doing, to make sure it makes sense to do a randomization test or a significance test, to make sure it makes sense. Okay, so you either do this, an imaginary large population of all possible Stat 100 students, and that's what we've been doing all along, from which 858 students were randomly drawn. Okay? The null is there's no real difference between the mean group attitudes and the whole imaginary population. And then we compute an F or a chi-square statistic and look at the sampling distribution under the null. Okay, because that's the assumption we're making. And this is what ANOVA is doing. All right? But there's another way to do it, and that doesn't depend on the assumptions I just showed you. You can imagine and think of an imaginary randomized experiment. Okay, so instead of sampling from a larger population, think about this, imagine a randomized experiment. And the null says that knowing which ethnic group someone is in tells you nothing about the person's attitude towards gay marriage, right? So if this were true, I could randomly assign the ratings among the 5 groups, and it wouldn't be surprising to get the differences we observe in our sample by random walk. So we can simulate doing this on the computer. That's what we're doing when we do a randomization test. And just like we did for regression. So this is what the randomization test is doing. It's making a randomized sampling distribution. It's simulating, making an empirical sampling distribution of the test statistic under the null. It's just saying, hey, remember what the null is. It says what ethnic group you're in this particular case, what group you're in, has nothing to do. It's completely unrelated to your quantitative variable, in this case the ratings. So it would be the same thing as just taking all those ratings and randomly dividing them into 5 groups. If you did that, just by the luck of the draw, random, all 5 groups aren't going to have the same mean, even though they came from the same population. No, there'll be differences between them. And that's what, so we'll say, okay, let's just do it. Let's just take all those ratings, and randomly divide them into 5 groups. And compute our test statistic, which in this case, the one we're doing is R. And then we'll do it over and over and over again, and you can create a sampling distribution of the R's under the null. It's an empirical one. And the reason that I love it so much is because it's very easy to see what's going on. You just take all the ratings, put them in a box, right? Pretend that. And you would just randomly sample out, just divide them into the 5 groups. And compute and look at the differences. And then see how weird it is to get that difference we got of 1.795 between one, just see how weird it is under the null. Okay? Okay. So the randomized, ANOVA assumes the first imaginary scenario, which requires certain assumptions to be met concerning the wider population in order for our chi-square NEF test to be valid. But the randomization test actually enacts the second imaginary scenario and has the advantage of being distribution free, meaning no assumptions about a wider population need to be met. for it to be valid. So it's a really great way to check. I mean, I'm not saying how do you decide whether to use one or the other? Well, if your assumptions are somewhat violated, this is a great way to check it, just to see if they agree. See, if they give you very different answers, something is wrong with these assumptions. Or with the randomization. You have to figure out what's going on. But usually, I would like to say the randomization test is more conservative, but not in all cases. Okay? So basically, that's what we're doing. Instead of using all this theory that you learned back in Stat 100, all this stuff about standard errors, sampling distribution, central limit theorem, all that stuff, how to get all that stuff which we're using when we do the F and the chi-squared and we're just going to do just a simple experiment like any kid could do. You could teach it to a 5th grader. I'd love to. You could watch it in slow motion and see what it does, and then you get an understanding. Why it's so great is you really get an understanding for what statistics is about, because the whole study of statistics is about measuring random variation. So in that regard, you really understand what a p-value means at a gut level. And so it's great to do even if you are doing all the parametric statistics. All right, so that's the idea. And so we can do it here. And so let's look. So let's do the randomization test here. And it's the same idea as what we did before. And we have 858 Stat 100 student responses on 2 variables. One categorical, what their ethnicity is, and the other quantitative, rating 0 to 10, where 0 meant you strongly favor gay marriage and 10 means you're strongly opposed. And here we have the 5 ethnic groups. And in this class there are 448 identified as white, 84 black, etc. And here's their average ratings. So we could see this was the most conservative and this was the most liberal. Right here, we looked at those two. So we want to know, are these differences in the average ratings between the ethnic groups real? Meaning, are they due to some particular cause, or just due to the luck of the draw? We saw that the correlation between them was this. The correlation between the predicted ratings, what we predict, like if we predict all whites had this rating, all blacks had this rating, etc. How does that, we looked at the correlation between that and predicting their actual ratings, between the predicted ratings, is this. That's fairly low. It's not that high a correlation. It's pretty low. But is it high enough to be statistically significant, which is another question. You might not think it's important, but it might be statistically significant. It was. We found it to be very statistically significant. Now we're going to do it by the randomization test. So let's test it by the randomization test. So remember, attitudes toward gay marriage are unrelated. That's R equals 0. Versus they're not unrelated, but you can do a better prediction by knowing somebody's ethnicity. So here's how it works. If there really was no relation, then we could expect to see any of the 858 ratings randomly assigned with any of the 5 ethnic groups. So in other words, what could we do? We could put all 858 ratings in a box. Let's say these are just numbers, tickets with numbers written on them. Shake it all up, and then randomly draw out the first 448 ratings and assign them to the white group. Okay? Because there's 448 in there. And then we could take the next 84 of these tickets, each with numbers, each with actual ratings, and assign them to the blacks, etc., 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 until the box is depleted. Right? And then we compute a p-value. Not a p-value, an R. We'd compute an R for that. We'd look at the correlation between how well the scrambled ratings how well the predicted ratings based on that random division into 5 groups, how well they correlate with the actual ratings. They were just done by complete random, you'd expect a correlation of 0. You're not going to get exactly 0 just because of the sampling distribution, right? And so then we'd do this over and over and over again, and you create the sampling distribution of R's, each based on a different scrambling. And then you see where our observed R is compared to that. And you see, wow, it's so far out, it couldn't have come by just random chance. Look, it's just so much more extreme than that. That's not random variation, just wouldn't give us that. So we see that it's very significant. And this right here is what we observed in our sample. We don't get that just by that extreme in R correlation. So you see, okay, the p-value is 0 because we didn't get any randomization that went out that far. Any R just by randomization. Okay? And do you understand that? That's the idea. The reason I'm spending a lot of time on it is just because it helps you understand what a p-value is. Because people do all this computing and stuff of them, and then they can't really explain what it is. They just know 5%. Why 5%? Well, what does it even do? What it means is that when the null is true, the likelihood that you'd see such an extreme or more extreme as your test statistic that's what the p-value is. Okay? And R here is positive, so that's why they're all in one direction. So now, I think that I think this is a useful summary, so we'll just look at it and then we'll do a practice exam. So this term ANOVA is referring to 2 things. Usually people refer to this situation of comparing several means, like we've been doing. But also analysis of variance, which is also called ANOVA, is the procedure we've been doing of splitting the variation of the total variation of the y's into 2 parts, into a signal noise, a model, and error. And so here's your chi for both of them. Basically, here's your chi-squared and F statistics. And it's just, what are those? Those are just the test statistics we use to find p-values to answer the question, is our sample signal big enough to reflect a real signal in the population, or is it just due to chance variation? That's all this is doing. And they're going to yield extremely similar p-values. Why I like this one is just because it's simpler to compute. You don't have to worry about all those little degrees of freedom. But the software, and this, as n gets big, this will converge to that. But the software always makes you do this one, or that's just because it can. It's a computer. It doesn't care if it's intuitive or not. So I want you to know how to do that one, for large samples too. Okay? But they're the same idea. The idea is just they're dividing into 2 pieces, r squared and 1 minus r squared. All right. And this difference is exactly the difference between z and t-test. There's another reason why I like to do z-test, because you make an approximation with z-test. You don't have to worry about the degrees of freedom. And nobody does once they, in their head when you get a large sample. You don't even think about it. But the software always makes you do these t-tests, and of course, if you want to be a little more precise, you do those. Question? When the null is true, the mean of the F distribution is very close to 1. It's a tiny bit bigger than 1. But it's very close to 1. But the chi-squared is the number of degrees of freedom. The number, you can see why, because the degrees of freedom for the chi-squared, we'll go over that in the exam, okay? Yeah, the test statistics look different. They're not going to approach each other. They're not going to look at the same, but the p-value is. That's just because this one, f, is normalized, so its mean is 1. And this isn't normalized, so it's mean is its degrees of freedom. You don't divide. The number of parameters minus 1 is its degrees of freedom. You divide by them here, you don't here. So the f statistic looks smaller just because it's the test statistic itself, but they're giving you the same information. All right, let's do an example. So this yellow probably doesn't come out good, so I printed it out here. So let's do this. I don't think it'll look good on the document camera. I think this looks better. All right. So, you've had this problem so much. This is a very standard problem you've had. Just to make it really clear. You've had this on homework, and it's been on all your practice exams. There's 3 practice exams. There's this one. There's another one online that I told you about. I sent in the email, and it's on Compass Announcements. It's the one from spring 2017, last year. Do that one too. And then there's another one from, I think, a year and a half ago on, and that's your on lawn capital. So you have 3 practice exams. If you do all 3 of them, you should be in excellent shape. All right. So we're just trying to fit the simple, that just means 1x, simple linear regression for the whole population. Okay? And that means we can do either z and t or chi-squared and f's. If we have another x, we can only do these 2, chi-squared and f's. Okay? And even though we have a small sample here, I want you to just work through all of them. Okay? To see the relation between them. All right. And so we have this small sample. Let's get a highlighter here. So this is what you need to do these. You have to figure out the number of parameters here, which is just 2. Remember, this error, and it's just the intercept and 1x. So we have p equals 2. Okay? And what else do you need? You need your r, the r, and you're given that. All right. So I think the easiest thing to, well, here I ask you to do r squared. This is just so I give you 1 point for this, and then 1 minus r squared. You might not always be asked to do that, but in this exam I was. All right, I did ask you for it. Okay, now the easiest one, you're supposed to compute all of these. I think the easiest one to do is the chi-squared, to start with that one, because that's just r squared over 1 minus r squared. All right? Now, if you're just given this, the most common mistake everybody makes is they forget to square it, which is why I started putting, why does this look so bad? So if you don't forget to square this, even if I don't ask you for this, hint, hint, don't forget to square this, okay? So it's r squared, for the chi-squared here, it's r squared over 1 minus r squared times what? N. And that's your answer. And you're going to have to show work, by the way. I'm asking you to show work on all this. No work, no credit. We're just doing this because people are just doing all sorts of things. And I just want to make sure that it's to guard, it's for a number of reasons. To give you partial credit, but also because I can't tell how you got your answer. If you didn't, you know, people have all sorts of things in their calculator, or they're copying off of other people. So please, we're just not going to give you credit. If it says show work and you don't, you get 0. You'll get a 0. And not only that, you get your exam pulled out because it's suspicious. And because they're saying, why didn't they show work when we asked them to? So even if it's a super, super simple, like subtracting 2 numbers or whatever, show work, otherwise you'll get a 0. I'm warning you now. It hasn't been that way on other exams, so I'm making a big deal about it. All right, so we do that, and we get this 3.81. Well, now, this is just the square root of that. So if we take the square root of 3.81, and that's your answer here. Okay? It's easier to go this direction because, you know, if you did that, you don't have to deal with taking the square root afterwards is easier. I just think it's easier to go that way. Okay, same here. So now the f is what? R squared over 1 minus r squared. And now it's not not times 20. It's 20, what is it, n minus the number of parameters. So it's n minus 2. There's 2 parameters. Don't put n minus 1. That's when you're doing like a standard deviation, because you only have 1 parameter there. Then we have the mean. We have 2 parameters. We have to think of this as like a mean and a slope. We have 2 parameters. You have to do n minus 2. You all learned this n minus 1, and you think you just apply it. No, that's just when you're looking at when you're just dealing with standard deviation, when you're estimating variation around a mean. We're estimating variation around a line. Okay, so it's n minus 2. And then what's going to be in the bottom? P minus 1. So that's P minus 1. That's just 1, so you don't have to put it in. But for future, think of it as P minus 1. Okay? So if we had another x here, it would be 3 minus 1. So this is just, so now we get, when we do that, what I got was 3.429, and then you take the square root of that for the t. Okay? All right, now what? So that should be smaller than that. That's smaller than that. Good. So now we want to compute p-values. All right. So you have to look at, for the chi-square in f, the alternative is always this. It's not directional. It's always two-sided. But for the z and t, it could be one-sided. But here I say do two-sided for all. How do you know it's two-sided? Because I'm not telling you whether to look at the right or the left-hand tail. I'm just saying it could be either. It's just not equal to 0. So we're looking for what's the probability of getting this extreme or more extreme p-value in either direction. So either, okay? So what do we do? So here we just have to look up, this is the only one you really, so here I say label z on the north. Okay, so you know in the middle is 0. And now we're just going to say between 1.952 and negative 1.952 is 90, about 95%. That's fine if you round. And so then your p-values, because I said this, it's going to be, I didn't specify whether r is going that direction or this direction, so it's going to be 5%. Otherwise, it would be 2.5%. Okay? And so now this is 5% because the chi-squared always gives the same. As chi-squared is the sum of, look, it's based on r squared. This always has to be positive. So whereas this could come out positive or negative. All right, now this is the p-value for, this is always greater. And the p-value for f is always equal to the two-sided p-value for t. In this case it is. Otherwise the p-value for f would be twice as big as the one-sided. All right, and the p-value for f is, it's fatter in the tails. Fat tails means p-value measures the area of the tail. Fat tails, that's f and t, fat tails. So p-value is bigger. Okay, so that's the idea. Any questions on that? All right, and now what's the next thing? If you change the alternative to a directional alternative, well, then you just, greater than would be just fat tails. They would be divided by 2. If you said less than, it would be that tail, still divided by 2. To use the ANOVA chart to calculate f, you'd need to calculate SST. Well, I gave you this and this, so before, oh no, I didn't give you the SDYs, now I give you this. Okay, so what is SST? Well, that would just be what, 25 y25. So it's SST is going to be SD of the y's squared, right? That would give you the variance, and then you have to multiply by n. So in this case, it's going to be 5 squared times 20, which is 500. All right, does that make sense? And then what is SSM? Well, remember, SSM is what? It's, R squared times SST is equal to SSM. That's what we've been doing all along. So where's our R squared? We have it as 0.16. So that's the proportion that's explained, and that's 80. All right. So any questions? Let's go move on then. Okay. All right, so these 4 plots depict data from 4 populations, and we're trying to figure out if X causes Y in these 4 populations, and each plot consists of these 2 groups, males and females. Let's focus on the relation between X and Y within each group. So within each group, they're all positive. Is there the same strong positive relation? Yes, they all have the same slope. There's no interactions here at all. Now let's focus on the overall regression effect. For which plot does the overall regression effect agree with the group of regression effects? Well, certainly that one and that one, right? So that's plots 2 and 4. Now, in which plot is there an interaction? We just said none. In which plot is the overall of X and Y confounded because of gender? So if the overall, which you can see, if it's equal to the 2 group averages, like here it is, and here it is, but here it's not. The 2 group averages average out to that. So it's confounded in plots 1 and 3. Okay, any questions on that? You should really do some of the homework on this because I think that it would be important. For example, let's look in our notebook here. When we first started doing this, here on page 77, right? Like this question was a homework question. I strongly recommend you look at that and review that. This question in your homework. It's on page 77 in the notes. Okay. Now, this one everybody understands really well. Do you want me to go over this at all? Do you want me to skip this one for now so we have time for everything and then go back to it? People just seem to have a very easy time with this one. This is question 3. Or do you want me to go through it? Raise your hand if you want me to go through it. Okay. The middle one? Okay, we can go through it. Okay, so what are we trying to do? We're trying to match this with these results, right? There are 2 drugs. Okay, so A and B are both 0. So when A and B are both 0, that has to be 2. And as you go from here to here, this is 3 when you just had, when you introduced A with B still 0, right? And when you introduce B, 2 plus what? 4 gives you 6, right? And there's no interaction. There's no interaction. So 5 plus 4 must give you 9, or 6 plus 3. And if you want to, if that's too confusing, just put a 1 in here and a 1 in for there, and 2 plus 3 plus 4 is 9. There's no interaction. You see right here in this spot, A is 1 and B is 1. So plug in a 1 and a 1, and that will give you your answer. Okay? Now let's do this one. The middle one here. So now what are we supposed to do here? There's only an interaction. Okay, so let's plug in. Here we have A and B equal to 0 again, so that's 2. There's only an interaction. So when A is 1 and B is 0, when A is 1 and B is 0, what do you get? You just get 2 here. If either one of these is 0, you'll just get the 2. And now, when they're both 1 here, put a 1 in here. Well, that's all you needed, right? Because this is already 7. You don't have to solve that. Okay? So there's just, oh, but you have to put this here. So now, when they're both 1, you have to put a 5 in there to get the 7. Does that make sense to everybody? All right. And then this last one, when they're all 0 here, you get a 0. When just B's 0, you get a 5 here. When A's 0, you get what? 6. And then you put 1s in for all of them, you get 9. Okay, let's go to the next. Okay, so is this, did I change this problem? Let me look in your, hold on. Let me look in your, somebody said I changed one of the problems and didn't have it on the key. Oh, this is right on the key. Okay, so we have on the key, so this is 27.2 plus 1.61 times height. This is how you have it in your notebooks. And this is negative 116.7, right, plus 4 times height. That's what you see in your notebook, correct? All right. So now, and now we say translate. Okay, so you have to pay attention to this. Males equals 0. All right, so translate the two simple regression equations into a multiple regression equation. So here's for males, this is females and this is males. And when males, okay, and so males equal 0 for gender. So you just want to copy this for gender. When we put 0 in for gender, we want to get that. So let's just put that in. Negative 116.7 plus 4. Okay? So that'll give us, when gender is 0, that'll give us the male. Now when we put a 1 in for gender, we want it to match up with this one. Well, we put a 1 in for gender, and that's going to change the intercept here, because there's no variable here. Once you put a 1 in, there's no variable. So what do we want in there? Well, for females, what intercept do we want? We want the intercept, we want 27, we want a 27.2 in there, right? So to get that, we're going to have to add that, right? We're going to have to subtract that off. So our answer will be, we want to put in there, is 27.2 minus that. So that's plus 116.7. And that will go in here. That's 143.9. And same here. Now we want, for females, we want to get 1.61. So let's just write, that's what we want. But we already have this. So we want to subtract that off. So 1.61 minus 4 is negative 2.39. Does that make sense to everyone? All right, so now if we switch the code around the other way, what are we going to do? If we switch it around, now females are 0. So we want to copy down the female one right here. So we'll copy that down, 27.2 plus 1.61. And now we want to get males for gender. So we want to get that. So just write that down. That's what you want. 116.7, but we already have that, so we have to subtract that off to the intercept, and I got -143.9, and notice they're just going to be opposites of each other, and this one will be the same thing, just opposites of each other. We really want 4 in here, so we have to subtract off that, and you're just going to get the opposite of that, 2.39. Now, when the null hypothesis is true, with 8 parameters in large N, you'd expect your F statistic to be about 1. The mean of the F will be about 1. And you'd expect the chi-square statistic to be equal to, it's actually equal to, the mean of the chi-square distribution is equal to its degrees of freedom, which is equal to P minus 1. So that would be 7. Alright, so let's turn this page. Do you have a question? Yeah. This one to be about 1? I mean intuitively why or what? Or well, intuitively why it makes a lot of sense is because what the F is the ratio of, like, it's sort of like 2 ways of estimating the variation of a population. One is by, it's the ratio of their, the sum of squares, the variation due to the model, explained by the model, and variation explained by the error. And when the null is true, there really is no model. So it should be, those 2 things should be the same, the error and the model. So it's a very, I mean, this is, I like the F because it's more intuitive to think of it that way. This is, and it was designed to do that. That's why you divide by P minus 1, to make it at 1. Otherwise, it looks like this. It would be 7. All right. Questions? Any more? Oh, that is so hard to see, but you have it in front of you. Why is this so? I'm wondering if I just zoom in and do the usual, if it's going to make it any better. And then zoom out. Okay. Anyways, last survey yielded this multiple regression. The number of piercings people have is related to their gender, negative 0.1 plus 1.34 times gender plus 0.6 times the number of tattoos they have, based on 231 responses from Stat 200 last semester. How many piercings, how many tattoos, and what's your gender? Okay, so now we're doing this kind of imagining that they were drawn from a much larger population. All right, so the above equation describes what? Well, you have 2, it's an equation for it would be a plane. Think about it. 3 points determine a plane. You have a piercing, a gender, and a tattoo for people. 3 points determine a plane. Okay, and it's the best fitting one to minimize the squared errors in Y, so in the piercings. And so what does the slope mean for gender? It's if for people who have the same number of tattoos, remember, it's how much gender is going to influence their piercings, controlling for that. So for those with the same number of tattoos, females have 1 point. So you compare a male and a female with the same number of tattoos. So the multiple regression for all students with tattoos equals 5. Well, this is just plugging in 5 there. So you get 5 times 0.6 is 3. So here you get, you'll still have the 1.34 times gender, but that would just change the intercept from 5 minus 0.1. I mean, 5 times 0.6 is 3 times, right? So that's 2.99. That's times 5 minus 0.01. Okay? Now, comparing two people of the same sex who differ by 5 in their number of tattoos, how much does the regression estimate they differ in their number of piercings? Well, that's what this tells you. 0.6 for each tattoo. So if they differ by 5, that's what the slope says. That's for each extra tattoo that you have, you're going to have 0.6 more piercings. So if you have 5 extra tattoos, you'll have 0.6 times 5, 3 more piercings. Okay, comparing two people of the opposite sex. That's of the same sex. But now you have to opposite sex. So now their gender is different and their two tattoos are different. So we still have the 3. Comparing two people of the opposite sex who differ 5 in their number of tattoos, how much does their regression estimate they differ in the number of piercings? Well, if the female has 5 more piercings than the man, she'll have 3 more tattoos, right? I mean 3 more piercings, excuse me, I screwed up my... If she has 5 more tattoos, she'll have 0.6 times 5, which is equal to 3. That's just if she was the same sex. But now she also, women have more piercings. I guess they have a lot of pierced ear. She also has going to have more because they're going to differ by 1 here. So it's going to be plus 1.34. So that's 4.34. If the male has 5 more tattoos, well, he'll get the same advantage of the 3 for the tattoos. That's, I don't know if it's advantage to have more piercings, but he's going to have more piercings, your best estimate. But now he's going to have a 0 instead of a 1 in here, comparing it to a girl, so you have to subtract off that. The guys don't have as many piercings. And that is 1.66. So that's just simple interpreting slopes. Okay. Now, do the F-test for the overall effect of the model. Okay. This is what you need to know. Right there. So you say 0.7 squared over 1 minus 0.7 squared. Now, where's n? N is 231, and you have to subtract off p. And in our model, now what's p in our model? 2 slopes and an intercept. So you have to subtract off 3. And so you have to have 3 minus 1. Okay? So just think in your model. Just get that p down first. What's your model? And then just pretty easy. Okay? And I did that, and I got 109.53, which is huge compared to 1. You'd expect 1. Look at the F table. Okay, so I'm asking you to look at the critical value. So you have to know where to look. So there's 2 degrees of freedom for the model, even though it's here in the denominator. Those are associated with the model because those are the number of parameters right here is our model. It's in our model. That's our model. Inside our model. So that's the degrees of freedom for the model. So you have to look at degrees of freedom for the model is equal to 2. And the degrees of freedom for the error, well, remember every person has an error associated with them. So it's 231, but then we have to, degrees of freedom, how many are free to vary? After we know 3 of them, only the rest are free to vary. So it's 231 minus 3. So that's 230. So now we know where to look. And then we're going to look at the critical value at alpha equals 1%. So let's do that. So we go to our table, and one of them here, you'll have this same on your exam. So here's the one we want to look at. And we want to look at what? Degrees of freedom in the numerator was 2. And in the denominator, was 228. So go to the more conservative one right here, the smaller one, and this right here is what we want. Okay? So I direct you to do that. Use the line with the smaller degrees of freedom. Yeah. All right, so it's 4.7865. So that's where we got it. Sorry. 4.7865. All right. Suppose you decided to reject the null. Oh, wait a minute. Our F stat is much bigger than that. Like, it's huge. It's way off scale. So our p-value is much smaller. Much smaller. Remember the picture. It's like way out on the tail. The tail's almost non-existent. Look at that. It's a huge F we got. Look at that. It's well beyond what we'd expect. Remember, we'd expect 1. Look at this. And anything beyond 4.7865 is significant at the 1% level. All right. Suppose you decide to reject the null. What would you conclude? The null says all the slopes are 0. There's no model at all, so at least 1. Either the gender or tattoo or both. Okay, to see which is significant in the multiple, you ran a z-test and a t-test. Which is which? Which test would you expect higher p-values? Well, the t-test is fat in the tail, so it's going to give you a bigger p-value. How many degrees of freedom for the t-test? The t-test, remember, that's based on every single point again. It's like n minus, it's usually when you did t-test before it was n minus 1, but now it's n minus p because you have more parameters in your model. You used to have just one n minus 1 when you just had a mean in there. All right, so now it's 220. It's every person 231 minus the number of parameters. It's the same as the denominator for the f. Okay, so the computer ran two-sided significance test and found they were both significant at alpha equals 0.2. Two-sided. Translate these into confidence intervals that give the same exact information. Two-sided, right? And they're both significant. 2% out here, that means 98% in the middle. So, the same information, they're either here, that means the same information that they're significant means they're outside the middle area of 98. Which means what? That your confidence interval did not include a 98% confidence interval. Zero's in the middle, does not include 0. Because we'd expect no difference. 0. All right. Another variable is added to the model that's negatively correlated with piercings. I don't care if it's negatively or positively. R squared has got to go up or stay. If it's correlated at all, R squared is going up. If you add anything, the only way it would stay the same is if it's uncorrelated. If it's negatively or positively correlated, it's going up. Let's say and the slopes for genders, okay. Let's say a third variable that's correlated with piercings is added to the multiple regression. Correlated with y, yes. And the slopes for gender and tattoo stay the same. Well, then it's uncorrelated with those x's. So the only way they're going to stay the same is if it's uncorrelated with the x's. Okay, how is the multiple correlation calculated? It's always the correlation between your actual and your predicted. Correlation's only defined on two sets of numbers. So you have to get one set of number, the predicted, and another set of numbers, their actual. And it's the correlation between those two. That's all you can do with multiple regression. This makes no sense. No sense. Correlation has to be just on two numbers, test sets of numbers. Okay. Let's see. All right. So now we've got these group differences again, how strongly these different groups believe in God. And now I want you to do an ANOVA table here from them. Okay, first assess whether any of the differences are significant. And I gave you this and I gave you this. All right, so this sum of squares model, or between plus within, has to add up to that. So this, it has to add up to that, so this is pretty easy. Degrees of freedom. Now, remember, P and G are your number of groups. P is equal to G, the number of groups, which is equal to 1, 2, 3, 4. So we're just doing our usual thing. And what's N? N is 230. All right. So this is N minus 1, right? For your error is N minus P, which is the number of groups. So that's going to be minus 230 minus 231 minus 4. So that's and this is P minus 1, G minus 1, which is 4. And make sure they add up. They do. So now this is super... Oh, they don't. Duh, don't make that mistake. Thank you. Thank you. Sorry. Okay, so now, what do? We divide. It's almost 300 divided by 3. So we're almost going to get 100. So this is, can I just give you the, you understand how to do these, right? And now you have this divided by that. Divided by that, and I got 11, 17. And then F is going to be the ratio of those two. I got 8.923. And this is the square root of that. And how do you get R squared? R squared, remember, it's a proportion. It's going to be, it's given to you right here, 229 over 2835. It's the proportion, remember, R squared times SST equals that. All right, so now, so SST is SSB over SST. You've got that. Now, what's the p-value closest to? Yeah. What did I do? Oh, damn. Oh, sorry. I mean, thank you. So easy to do. I'm just looking at the time here. Thank you very much. Sorry. Okay, so now what are we going to do? We have to look at this F and with the degrees of freedom. Do you know how to do it now? Do you want me to go? Because I want to get to others. Tell me, do you need to see this? I think you're good there. I think you're good there. What's the difference between, what's the standard error of the difference? Okay, and I wanted to say plus of the difference. What is that? So we're going to use this that 3.34 times the square root of 1 over their sample sizes. And what are we looking at? White is what? The sample size for white is 44, and the sample size for East Asian is 133. Do you understand that? Okay, now, let me get some number here. I got 0.581. Now the t-statistic, this is really just observed, just the difference between those two. All right, and it's non-directional, so you might as well just use the positive difference. So that's 5.3 minus 3.7 over that. And I got 2.75, and the degrees of freedom is the same as you got here. All right, the p-value is about that. Now, the Bonferroni is going to change it by the number of groups times G minus 1 over 2, and we have 4 times 3 over 2, right? So that's 6. So you multiply that by 6. So it's just going to be 6 times 0.58. And we get 3.48, and it lowers the probability of making a false claim, of saying you see a difference when false alarm. It lowers the probability of false alarms. Of saying, hey, I see a difference, when you really don't. Okay, when there really is none. Are we on our last page? Yeah, good. Now this randomization test, we just did it. Okay, so there's another way to do this whole thing, the randomization test. And how is each randomization done? Now, you should know this. How is it done? Those actual ratings were randomly distributed among the 4 ethnic groups. Yeah, that looks right. Wait a minute, maybe it's not. Let's see. Read all of them. The 231 were randomly assigned numbers, no. The random numbers, no. They were randomly distributed among the 4 ethnic groups, keeping those numbers the same. It wasn't like they made 4 even groups. But this is the only one that makes sense. Okay, this vertical line is our sample, R. So what is that? How does it give the location to 3 decimal places? Well, it's nowhere here. We have to look at our sample R. We have R squared, but we don't have R, so we have to take the square root of that. And check, when you do that, that it makes sense. We got 0.325, and that looks good. You did something wrong if it doesn't line up right. Okay? So that looks good. That's 0.325. What does the area to the right of this represent? It represents the percentage of randomized R's we obtain as big or bigger as the R we obtained from our survey, yeah. The p-value given by the f-test, no. The p-value given by the randomization test, yes. Now, 30 numbers were divided into 3 groups of 10 each. The 3 group means are that the overall mean is 0. Which of the following do you have enough information? Well, you know the means. You have this one, right? For each of the 30 numbers in group, they're divided into 3 groups. So for the 10 in group, the first group, the group mean is 1 minus 0 for 10 of those squared, plus 10. There's going to be 10 in the next group, which is, they're all going to be predicted to be its group mean, plus 10 in the next. So whatever that is, I got 380. So many people put 3, 3, and 3, just because that's, I don't know, 3, no, there's 10 in each group. Remember, when you're doing sum of squares between, you have to get one for everybody, for every point. Okay, if there's no difference between the groups, there's no difference between the group means. That's what that measures, the difference between the group means. Then they all have to be the same. All the group means are the same. They don't all have to be 0, but they all have to be the same. That means there's no difference. If the sum of squares between each group is 0, that means there's no difference between the groups. If the sum of squares within is 0, that means there's no spread within each group. So every single point is at its group mean. The numbers within each group are the same. Yeah, there's no spread. The group mean is, they're all the same. Okay, so that's pretty much it. That's it. And I have office hours today from 4 to 6. If you have questions, come by. No office hours tomorrow. My strongest recommendation is to do all 3 of the practice exams and do the one online multiple times with different numbers. And do them as real exams.